Hi everybody, today we're going to be doing the M4 practice hackathon. In this hackathon, we'll be creating a classifier model that will help us predict whether the client of a bank will be likely to default on their loan or not. So to create this classifier model, first we need to import the necessary libraries such as NumPy, Pandas, Seaborn, Matplotlib, etc. We'll be loading in the training dataset from the Kaggle website. As you can see over here, the data set has many variables such as person's age, gender, education, income, home ownership, yes or no, etc. And we'll be using all of this data to create a classifier model. First of all, it's important to inspect the training data set. So let's see what kind of columns we have. So we have in total 13 plus 1, 14 columns. And then we have no null values. That is great news for us. That means we do not need to get rid of any null values. And we can check the data type of each of the columns, which is very important because sometimes machine learning models read data types differently, which could lead to different outcomes. So let's load in the test dataset as well, which is the same, except we'll be not touching the test dataset and only be using this for prediction purposes. And the first step is always to make sure that the data is clean, transformed, and normalized so it can be effectively used for classification purposes. So first, let's check for class imbalance or skewness. So this is vital for maximizing F1 scores because having a skewed dataset can cause the model to predict wrong. So there are definitely some classes that have skewed data. Example, the income distribution is definitely skewed. So as we can see, the income distribution is extremely skewed with high income outliers overpowering the rest. So this means the income will have to be log transformed to make sure the data is more normalized, and machine learning models can read normalized data better than skewed data, such as this one. So first, let's try implementing a short AutoML model. So AutoML models are basically machine learning pipelines that train and test and does everything with your dataset from beginning to end automatically. And the AutoML model we'll be using this time is called the H2O. The reason we're using the AutoML is to understand what kind of models perform the best so we can focus on that specifically in the future. So first of all, we need to log transform the data set, some of them, especially like the person's income. Then we need to set up the target because H2O cannot read in the normal pandas dataset. We need to transform that into a readable data frame called the H2O data frame, which we do here. And we also implement a 5-fold cross-validation method. This means we don't really separate the training dataset into just a training and testing split of 80-20, but we split it into 5 different folds, which will be cross-validated against each other. So as you can see, the H2O is running, and it gave us a cross-validation metric summary over here. So it gave us an F1 score of 0.83 mean, which is pretty good. So the mean is basically the average of all 5 folds. And you can see there's also standard deviation, which is pretty small, meaning all of the folds performed almost as equally well. So for our validation strategy, we actively chose to bypass the single train test split, as I already mentioned before, because in a financial risk context, a single 80-20 risk is highly susceptible to a lucky draw. For example, if all high income defaults happen to land in one training dataset, our validation metric will give us a false sense of security. Okay, next we're going to create a leaderboard, print the leaderboard, which will basically show us all of the best performing models that the H2O model was able to get. As expected, the first 5 models are stacked ensembles, meaning they're weighted averages of many different other models. These models are actually great in terms of accuracy and performance. However, they're black box models, meaning we do not know what's going on under the hood. And the reason we don't like to implement these models is because banking is a highly regulated industry where it's important to be able to explain how you got the data, because implementing certain features could be illegal or could go against regulation. Besides the stacked ensembles, we can see that the next best performing models are GBMs and XGBoosts. So in the future, we're going to be focusing on these types of models. So as you can see here, we found the highest performing models, which are the XGBoosts and the GBMs, and the worst performing models were actually the GLMs, as you can see in the bottom over here. So we're not going to be focusing on that at all. So this leaderboard directly justified our decision to manually build a k-fold variate and heavily tuned XGBoost for our final Kaggle submission. So first of all, over here, we're going to use a variable importance plot. This code handles cases where the leader model might be this code cannot handle cases where it's a stacked ensemble, so it's gonna handle all the non-stacked ensembles, so basically the XGBoost. So here we will see which variables are most important in the, well, for this case it's the GBM machine. So the most important variables were previous loan defaults, loan interest rate, loan percent income ratio, the personal income, etc. And there's also less important features such as a person's education, a person's credit history length, etc. So now we're going to be creating a manual XGBoost model using a 5-fold cross-validation method. So after reviewing the H2O AutoML leaderboard, XGBoost consistently ranked as the single best non-ensemble models. Now we're going to manually build an XGBoost classifier to have full control over processing. So we're going to have the key decisions over here. Estimators about 500, enough trees to learn complex patterns without underfitting. Max depth 4, shallower trees to reduce overfitting, because XGBoost performs the best around 4 to 6. Learning rate 0.05. Slower learning rate paired with many trees generalizes better. And scale POS weight of 3.5, directly addressing our class imbalance, because this tells us XGBoost to penalize missing a default of 3.5 times more than the missing a non-default. And a stratified k-fold n5 split. This ensures that each fold has the same class ratio, critical for imbalanced datasets. This returns train and test F1 so we can detect overfitting. So as you can see over here, we're also preparing the data for the XGBoost. We're importing libraries such as sklearn and stratified k-fold cross-validate. So here we also apply a one-hot encoding method to categorical features. We didn't do this in H2O because H2O does that automatically, but when we do this manually, we have to do all of it. Otherwise, the machine learning model won't be able to understand our data perfectly. And we also implement a 5-fold cross-validation method, again, which I explained, separates the data into 5 different parts. So here we can see the manual model gave us a cross-validation F1. This is a mean, by the way, of 0.8079 plus or minus, with a standard deviation of 0.0053. So now we're going to try implementing a learning curve to diagnose overfitting. A learning curve plots the training F1 and the cross-validation F1 as we increase the number of training samples. The gap between the two lines diagnose the model fit. A large gap means it's overfitting. Both lines are very low means underfitting, and if both lines are converging towards a singular point, that means it's a well-fitted model. As you can see here, both of the lines are starting to converge, but there's definitely still a pretty big gap over here. So to address actions to address overfitting were limiting the depth and limiting the learning rate. So now we're going to, since there's such a gap, we want to try to generalize better. So we're going to try feature importance analysis. So this will use XGBoost built-in feature importance scores to identify which variables drive lone default prediction and which are adding noise. So as you can see here, this ranks all the features from top to bottom, where top being the most important and bottom being the least important. So as you can see over here, previous lone defaults on file is still the most important. And it drastically drops into the next one, which is the lone person income. And a lot of these are mostly noise, such as person's age, person's employment experience, etc. Mostly noise. So now we're going to be creating a feature reduction model, a second model, which we're going to call XLean. So basically, we drop all the noisy features. We drop the home ownership, we drop the education, we drop the, all of those. And then we create a lean version. And we rerun a 5-fold cross-validation method again and see how it does. So this time it gave us a cross-validation F1 of 0.87, which is marginally better than the original of 0.8079, confirming that these 6 features were definitely adding noise than signal. That means they were not helping us generalize better. The reduced feature is cleaner, faster, and less prone to overfitting. So XLean is going to become our standard feature matrix going forward. So next, we're going to try creating another model. So this we're going to call the champion model. So this one is going to actually make copy of the XLean because we don't want to try from the old one. And we're gonna one-hot encode the categorical columns, and we're going to drop a bit more columns, as you can see over here. And we're going to actually try to process it and create this for the submission. So we submitted the champion file, and as you can see, this is one of our best performing files. So now we're going to try model comparison. We're going to try 3 different models, which is the logistic regression, random forest, and XGBoost. And technically we did 4 different models because we also tried the H2O. So here we can see we're going to do from the beginning: clean, log transform, scale, encode, and everything. So first we're going to make sure the skewed data sets are log transformed. We one-hot encode all the categoricals. We drop the low importance features as we did in the lean dataset, and we scale for logistic regression. As you can see, we changed the skewness a lot, such as the income skewness was 36, now it's 0.22, 1.8, negative 0.44, and so on. So the pre-processing pipeline. So first we log transform, and then we one-hot encode, and then we feature drop, and then we standard scale. Why do we do this? Because having a skewed data set splits LR assumptions. Converting strings to numeric is important because the machine learning models can't read strings. XGBoost importance scores less than 0.003. That's why we dropped the features. And tree models are scale invariant, so LR is not. So now we're going to try with another type of pre-processing, with LR using xscale, tree models using xfinal. So here we compared all the 3 models. So we're comparing XGBoost, we're comparing random forest, and we're comparing logistic. LR is logistic. So here we can see the cross-validation F1 of all 3 of them. The highest one is actually with the random forest. So interpretation and business implications. So logistic regression, fully explainable, fast. Random forest handles a little on linearity. XGBoost best for F1, but it slightly overfit sometimes. So for a business context, false negatives are really bad because we lose a lot more money compared to false positives. Rejecting a good customer is cheaper than lending money to someone who's likely to default. So for the next one, we're going to try XGBoost with scale weight 3.5 and threshold 0.66 to make model more conservative, meaning much more preferring to have a false negative than a false positive. So we're going to try a confusion matrix to see confusion matrix and precision recall curve to see how it's doing. So as you can see here, the confusion matrix is showing us the false positives and the false negatives, and the precision recall curve shows us how the curve is going down and the threshold over here. So our threshold is about 0.64. As you can see, this is the most expensive one and it is the lowest one, so that means our models are doing pretty decent. So false negatives drop, that means fewer loan approvals to people likely to default. False positives slightly increase, that means we are rejecting good applicants slightly more, but that's a necessary expense in my opinion. So the precision recall curve shows the trade-off across all thresholds. So red line marks the mathematically optimal F1, and which closely matches our chosen 0.66. So our decision was pretty near the mathematical optimal. So now we're going to create the submission file, which we will be submitting. And we also tried a few other types of submission files. So we tried 3 different submissions in total, and we were able to achieve a leaderboard position of 43, which is pretty good. So thank you very much for listening, and this is how we implemented different learning methods such as learning curves, confusion matrix plots, precision recall curves, and we were able to do hyperparameter tuning using different methods such as importance variables and plotting for the H2O gradient boosting machines, variable importance. So we compared with different models, and then we also got the best model, which achieved us final F1 score in the testing data set of about 0.86. As you can see here, the F1 data set in the testing is different from the F1 data set we got here from the cross-validation methods. That is because we were not really using the testing data set at all. We kept it as a black box method, and it's only testing within the training data set. So it's gonna give us a different outcome because this is a totally different data set. But anyways, thank you for listening, and it was great having you here.